Madison Company continuous level float switches are designed for vertical mounting in a tank. DC power is applied to the switch, which can then provide a 4 to 20 milliamps, 1 to 5 VDC, or a resistive output signal that can then be routed to programmable controllers, microprocessors, or other readout devices. A reed switch and resistor network is controlled by magnets in the float to provide a continuous output over a specified range of indication. These sensors provide a precise, uninterrupted output signal and can be designed with either 5 or 10 millimeter resolution. These sensors are custom configurable and can be coupled with Madison Company's full line of digital displays and controllers to meet your application requirements.
Capacitive level measurement offers a wide variety of possibilities for level monitoring in liquids and bulk solids. The space between two unevenly charged objects is called an electric field. In this space, one electric charge exerts a force on another charge. The strength and direction of the electric field is shown by lines of flux. If an alternating voltage is applied to a parallel plate capacitor, current starts flowing. The strength of the current depends on the dielectric material between the plates, for example, air or a medium. The dielectric material increases the capacity of the capacitor and thus the current flow. The principle of capacitive level measurement depends on capacity changes. This method takes advantage of the fact that products in tanks have a different dielectric constant than air or gases. To measure levels or limits, a probe inside of the tank and the electrically conducting tank wall form a capacitor. As the rising level covers the probe, the measured capacity changes and the cover is detected. As the level falls, the probe reports that it is uncovered due to the change in capacity. If conductive buildup sticks to the probe, this is recognized as a change in capacity in relation to air, comparable to a product. In this case, the lines of flux run directly through the buildup to the tank wall. Even if the product does not cover the probe, it reports covering erroneously. Endress & Hauser has developed a capacitive probe with active buildup compensation. The probe has an additional protective electrode with the same potential as the measuring probe, which not only generates one electric field, but two identical fields. The shielding effect of the active buildup compensation prevents a direct current flow along the probe electrode to the tank wall. Therefore, the current of the probe does not flow in the area of the buildup, but only in the area of the actual cover. This principle enables the probe to measure reliably, even in spite of strong conductive buildup. In radiometric measurement, the source is installed in a container. Radiation is emitted during operation. The compact transmitter detects the radiation on the opposite tank wall and converts it into an electric level or density signal. The radiation can only be emitted in one focused direction and is screened in any other direction by the source container. For optimum adaptation to applications, the FQG61 and FQG62 source containers are available with different screening effects and emission angles. The device can be switched on and off by a 180-degree turn of the source holder. This rotates the source in front of the emission channel in the on position. In the off position, the screening material covers the source and also prevents the emission of radiation towards the flange. The off position is needed during transport or if the tank or reactor must be accessed for revision purposes. The on-off position is optionally fixed by a lock or locking bolt. Radiation can only be emitted if the source is in the on position. The unambiguous fixation of the position guarantees safe operation. Radiometry is implemented where other measuring principles are excluded due to extreme process conditions or mechanical, geometrical, or constructional circumstances. Radiometric instruments are used in point-level measurement as well as continuous level, density, and interface measurement. The field of application for this non-contact measuring principle comprises liquids, solids, suspensions, as well as sludges. Your partner, if high measurement availability and reliability are needed. Andrus and Hauser. In level limit detection, fast, safe functioning and availability are of high importance. Small problems can cause devastating effects. Liquefat, the active level limit detection with a safety window. A sensor in form of a tuning fork is excited at its resonant frequency. The drive works piezoelectrically. The oscillating frequency or the amplitude changes as the fork enters the medium. The change is analyzed and translated into a switching signal. In case of emerging air bubbles or foam, Liquefat recognizes the medium differences and thus the actual liquid to be measured. Liquefat can be used in all pumpable liquids in a universal manner. Even in build-up conditions, level limits are safely detected. If mechanical damage occurs on the process side, the second line of defense takes over. A pressure, gas, or diffusion tight feed-through reliably prevents the medium from escaping into the atmosphere in case of a failure. Liquefat permanently monitors the oscillation frequency, thus providing a reliable early warning system in case of malfunctioning. Level measurement according to the time-of-flight principle is one of the standard methods in the process industry. Apart from instrument properties, the analysis of the echo signal ensures the safety and reliability of the devices. In traditional time-of-flight measurements, a pulse is emitted, reflected by the surface of the medium, and received again. The analysis is realized on basis of the echo signal curve. Obstacles in the radar beam, for example installed instruments or heating coils, generate an interfering echo signal. These obstacles are traditionally excluded from the echo signal analysis based on a mapping functionality. Only signals protruding over the suppression curve are accepted as level signals. If the level signal ranges below the mapping curve when filling or discharging a tank, incorrect analyses may occur. The signal then jumps erroneously, for example, to a so-called double echo, which follows the actual level echo at twice its distance. After the level has passed the obstacle, the echo jumps back to the correct level signal. Next level instrumentation. Andrus and Hauser has developed a more intelligent and reliable echo signal analysis in its new instrument generation, called multi-echo tracking. The new multi-echo tracking uses the echo signal curve for its analysis too. If obstacles protrude into the signal path, these baffles also generate a corresponding signal. As is the case in traditional methods, The mapping is also superimposed in multi-echo tracking. What is new, however, is that all of the echo signals are marked. The innovative multi-echo tracking of Endresen-Hauser pursues all marked signals, not only the level signal. The new analysis also detects the level signal if it ranges below the mapping. This guarantees safe and precise measurement even in the presence of obstacles in the tank at any time. If you compare both methods, it becomes clear that only multi-echo tracking of Endresen-Hauser leads to stable and safe output signals by marking and pursuing all of the echo signals. If you examine a filling or discharging operation as recorded in the control system, it becomes apparent that the traditional analysis leads to unstable measured values. Only the new multi-echo tracking of Endresen-Hauser provides a stable and reliable measured value signal.